Welcome to Math 2318, Section 2.5. In this section, we're looking at a particular factorization of matrix A. This is called the LU factorization. It factors A into a lower triangular and an upper triangular matrix. So for example, here's matrix A. It's been factored into L and U. So let's look at L. L, the lower triangular one, has ones on the main diagonal, zeros above it, and is lower triangular. Matrix U is upper triangular. The diagonals do not need to be ones, and we have zeros in the lower part. So in problem 1, we're going to use the factorization to solve a matrix equation AX equals B. And we're going to solve it in two stages. First off, we're going to solve Ly equals B. We're going to solve it for y. And then we're going to solve Ux equals y to get the x. So let's see, what does all that mean? Alright, so here's Ly equals B. Here's my lower triangular matrix. Here's the B that was given to us. So we're simply going to use row operations here, alright, to solve for y. So I'm going to use the 1 to make two zeros. I then will use this one to make a 0 under it. And so once I've done that, we have reduced it, and so I can see that y is minus 14, minus 3, and 5. So now I'm going to take that answer, and that answer, the minus 14 minus 3, 5, becomes my new right-hand side, and I'm going to solve for x. So here's U, my upper triangular matrix. We do the same situation of making ones and zeros. I'm just going to stick with this 2 for now because I don't want to make fractions everywhere. Alright, so first off, I'd like to have a 1 there, and I can make this 1 simply dividing by negative 2. And let's see, the last row already looks quite good. Alright, so I'm going to use this 1 to make a 0 above it. So we did that. Still leaving the 2 there for now. And then finally I'm going to use this 1 to make a 0 in this position. And so now that I've done all that, I can easily divide by 2 because I don't care about fractions at this point. And so we solve it and we get the particular x that we were looking for. Now the problem says, okay, solve it without trying to find the factorization first. And so here's A. I'm just going to use this 2. Again, I don't want to create fractions. So I use the 2 and make two zeros. I don't really want to make this a 1 because I'd have ugly fractions. So I'm just going to use this and make a 0 underneath. Alright, I notice at that point I can make this 1 easily enough, and I can use that 1 to make a 0. Once I've made that 0, I can divide this row by minus 2, so that looks better. I'm going to use this 1 to make a 0 above it. And then finally, kind of out of the normal way, but it just seems to work to avoid making fractions, I then use this 1 to make a 0. And then finally, in the very end, I can divide everything by 2. And I get that x is 2, 4, and minus 5. The same solution we got previously. All right, in question 2, we have matrix A. We have its factorization into L and U. Same process. We're given a B. We'd like to solve AX equals B by using my lower and upper triangular factorizations. All right, so here's L. Here's my B. Use the 1 to make 2 zeros. Use this 1 to make a 0. And at that point, I'm going to use, so that made a 0. And when I did that, then this term is 0. And everything else is cleared out. And so I get that y is 9, 12, and 0. That becomes my new right-hand side with my upper triangular matrix. In this situation, everything is divisible by 3, so divide this by 3. I can divide this by 3 as well. And now I'm going to use the 1 to get rid of the minus 2. Once I'm there, I then will use this 1 to make 2 zeros above it. And once all that's done, we get that x, our solution, is minus 5, minus 4, and 0. All right, in this case, A is larger. It is 4 by 4. I have my lower triangular, again, 1's on the main diagonal, numbers under it, zeros above it. And here's U. So I solve Ly equals B. So here's L, here's B. So just grind through this, use this 1 to make 2 zeros. I've got a 1 here now. Use this 1 to make 2 zeros. Alright, at that point things are looking pretty good. At that point I'm going to use this 1 to make this a 0. And once I've done all that, I finally can figure out the y that we're after. So I have y. And so now use my upper triangular matrix with the y for the right hand side. And let's see, what is there to clean up? Well, I can take this row and divide by minus 2. That looks good. I can use this 1 to make a 0. Let's see, once that's done, I then will use this 1 to make this a 0. And once we're there, I'll use this 1 to make a 0 there and a 0 there. And again, just grinding through all the row operations, or you can use Wolfram Alpha to row reduce it quickly. We figure out that x is 22 minus 11, 3, and 2. All right, in question 4, we have a problem that's going to help us determine how actually to find L and U. So what do you do? So here's matrix A. I need L and U. Well, what does L look like? L has got to look like 1's on the diagonal, a 0, and some number. Use on the diagonal a number and a 0. So just multiply this out. 1 times u11 plus 0 times 0. 1 times u12 plus 0. L21 times u11 plus 0. And finally, L21 u12 plus u22. And now simply match everything up. Well, u11 is 5. u12 is 4. Now we come to this product, which must be minus 4. But I know u11 is 5. So L21 is minus 4/5. And so finally I match up this sum has to be minus 3. So let's fill in what we know. This is minus 4/5. This is 4. I'm looking for u22. And so I get a minus 16/5. Bring it to the right hand side, a positive. Change this minus 3 to minus 15/5 and add them up. And so we get our lower triangular matrix and our upper triangular matrix. Certainly not as difficult as it seems. In question 5, we're going to do the same thing but for a 3 by 3 matrix. So here's A. I want it L times U. L, ones down the diagonal, and numbers under that. U's on the diagonal and numbers above it. So again, we just grind it out and compare. So 1 times U11 and everything else is 0. 1 times U12. 1 times u13. All right, so you can already see exactly what u11 must be. u12 and u13, they have to be minus 5, 0, and 2. All right, go to the second row. L21 times u11. And I won't bore you with the details, but it's just matrix multiplication down the rows and columns. And then it's just a question of not losing anything and filling things in. So for example, let's take this term. L21 U12 plus U22. Well, L21 we got from the previous one. 1, 2 was 0, and so that says U22 is 3. So essentially you're working from the top, and as you're gaining items, you're working your way down. Not hard, just takes a little bit of time. But in the end, we have our lower triangular and our upper triangular matrix. In our last problem, it's something from electrical engineering. We have some kind of electric circuit here. So here's our circuit. And in this circuit, we have some input terminals. We have some output terminals. There's a current going in and a current going out. You could consider this a black box. There's a voltage across the two input terminals, and there's another voltage on the output terminals. You can model this by the output, the voltage and the current that's coming out is a transfer matrix times your two input values. And in this particular homework problem, we're just looking at resistors. If we have a resistor in series, then that situation has the transfer matrix to look like the following: a 1, a 0, a 1, and whatever our resistance is in ohms on this particular part. If we have what's called a shunt or a resistor in parallel, so for that situation, the transfer matrix for the shunt is 1's on the main diagonal, 0, and a negative 1 over the resistance for R2. So a little bit of background knowledge. All right, in question 6, the situation is the following. We have 3 resistors in parallel. Each one of these has a transfer matrix. And so we just take it from what I just talked about. For the first one, we have a minus 1 over R1. For this one, we have a minus 1 over R2. And for the last one, minus 1 over R3. So those are just simply our 3 single shunt transfer matrices. All right, so if you trace through what's going on, an X goes into A1. It produces an output. And then A2, the next transfer matrix, takes over and continues until finally, to get through the whole electrical circuit there, it's A3, A2, A1. And so let's see, what does that actually look like? Skipping downward here. So A3, A2, A1. So what did I do? I left the first matrix alone and I did A2 times A1. And it's simply a normal matrix operation. 1 times 1, 0 times minus 1 over R1. So that's just a 1. The only thing interesting is minus 1 over R2 times 1 plus minus 1 over R1. And so here's our transfer matrix for A2, A1. And if you multiply by A3 now, you get a similar situation of minus 1 over R3 minus 1 over R2 minus 1 over R1. Now, we need to do a little simplifying on that, because if you remember, for our shunt matrix, we had the situation for the shunt. It looked like 1, 1, 0, minus 1 over R. So what I'm looking to recognize is, what is this R? So I get a common denominator and combine these. All right, so by doing that, this one needs an R2 and an R1, and so you get a common denominator. Now I want to recognize now that this item is minus 1 over something. Well, 1 over what? Well, first off, when I take the minus out of the top and flip this thing, we see that the resistance follows this particular formula to find the resistance of this electrical system. So an interesting way to look at something from electrical engineering.